I'm Mick Wijnen. I'm the CTO and co-founder of IENAI Space. And today I'd like to present our company as well as talk about ATHENA-π, which is our electrospray thruster for Pocketsats. IENAI Space is a young startup that's founded 2 years ago. We're based in Madrid in Spain. We've grown to a team of about 12 people now that range from propulsion specialists, electrical engineers, mission analysts, to system engineers and financial specialists and software engineers. And we have the backing of several institutions in Spain, such as the government, the university, research centers, and also 𝗖cie, a big incubation center. So what is it? What is the problem we want to solve in IENAI Space? And it's very well summarized in this graph here, where you can see the number of, in this case, nano satellites launched over the last 2 decades. And you can see it grows exponentially. But there is this line here at the bottom, which is the number of satellites that is launched that have a propulsion system on board, and it's lagging behind. And our goal is to close the gap between those 2 lines. So here you can see it summarized better. The adoption rates for nano satellites are about less than 6%. That's what they used to be. It grew to 12% in 2021, but it's still far off compared to microsatellites and medium satellites. And if you look at the Pico satellite class, it's far worse. So this is the problem we're trying to tackle. So why do we think that there is a barrier to mass adoption in these smaller satellite platforms? One of them is the platform variability. So both nanosatellites and pocket satellites, they come in many different sizes with very different power budgets depending on the amount of solar panels they have available. And in this case, the one-size solution that many traditional propulsion providers have doesn't fit. So this was our team that I mentioned. I have 12 people. This is the graph that I was just talking about. And as you can see, the exponential growth of satellites, nanosatellites launched. I don't have the same graph for Pocketsats, unfortunately. And here on the bottom, the line with the amount of satellites with propulsion on board. And what our goal is to close this gap. So here to recap these numbers, less than 6%, up to 12% now in 2021, and much worse for Pico satellites. So what I was explaining now is that what are the barriers to mass adoption according to us, which is the platform variability. And the one-size solution that is basically common in the propulsion providers doesn't fit all these different platforms, and there are no scalable solutions. Then there are the platform constraints. These satellites, both nano and Pico satellites, are very power limited, as well as mass and volume limited. And existing technologies, they don't scale down very well to these constraints. And the third reason is a lack of dedicated knowledge. Many satellite integrators and providers, they don't know exactly what their propulsion needs are. They don't know what they're looking for when they want to buy propulsion. And so this requires specialist profiles, both in propulsion engineering and orbital dynamics, which is very important when you want to choose a propulsion system. And this is very often lacking in small companies. So our solution to this problem is, on the one hand, ATHENA, which is our electrospray thruster. On the left, you can see the version for the CubeSat. And our other part of our solution is IENAI Go and IENAI 360. And this is a proprietary software we have. IENAI Go is free to use online web tool that you can use to size a propulsion system. So you, as inputs, you give the parameters of your propulsion system, such as the mass and the volume of your satellite and the amount of power available and the maneuvers that you want to do. And the tool will then calculate for you the optimal propulsion system. I will give a link to the tool at the end of the presentation. And then we also have IENAI 360, which is a more advanced mission analysis tool that we use to do mission studies, which we sell as a service to customers. So what is electrospray propulsion? In a nutshell, we have our core component exists of a microfabricated array of small needles, which we call the emitter, and a grid with small holes that are aligned with the emitters that we call the extractor. And when we apply a bias voltage between the extractor and the emitter, we can create a very high electric field that is concentrated at the tip of the emitter. And when we then feed our propellant, which is an ionic liquid, over the tip, we can create emission. And it's because the ionic liquid is an organic salt that is liquid at room temperature. and it has both positive and negative molecular ions. And so when these ions are near the tip of the cone, due to the high electric field there, you get something that's called field-enhanced ion evaporation. You liberate the ions from the fluid, and then you accelerate an electric field, and they are expelled through the hole. And you generate jets of very high velocity, up to 40,000 meters per second, and these jets is what generates the thrust. Apart from the emitter and extractor, we also have some flow regulation mechanisms, impedance control, and a 3D printed metal porous deposit for fluid storage. This is in a nutshell the concept of our Electrospray technology. So what is the advantage of Electrospray technology? Well, first of all, the ionic liquid. Ionic liquids don't have any vapor pressure, so we can store them in non-pressurized vessels. They're stable in vacuum. We can use passive feeding, so we can get rid of pressure vessels. We can get rid of valves and pumps that are necessary to for other kinds of propulsion systems. So this reduces the dry mass a lot and reduces complexity. Then our system uses electrostatic acceleration, so we don't have any magnetic elements such as magnets and electromagnets, and this also reduces further mass and power. And the other thing is that we can have zero net current. So before I mentioned that we apply a bias. Now, if you alternate the polarity of that bias, you can emit both negative and positive ions. And by doing this, you can have a net zero current, and you don't need a neutralizer or a cathode to ensure this, which is a limiting factor on lifetime in our propulsion systems. And the other thing, and I think the most important one, is the high efficiency at low power, because we don't use any plasmas. All the losses related to plasmas we don't have. And our technology has very high efficiency, up to 3 times higher than competing technologies below 50 watts. And our efficiency is also not dependent on the power level, because most existing systems, when you scale them to low power, their efficiency also goes down. So if you want to remember one thing about this presentation, it's that efficiency is a very important parameter for propulsion systems, because you see a lot of data sheets, they talk about ISP and thrust, but very rarely they tell you about efficiency. And efficiency is very important, because if your efficiency is shit, pardon my French, then your even if you have so if your efficiency is low, then either you're going to have shit performance at an acceptable power level, or your performance is going to be, when you have good performance in terms of thrust, you're going to have a power that dominates your power budget. So neither of those is desirable. So I recommend anybody who wants to buy propulsion to ask about the efficiency of the system. So now on to the interesting stuff, which is the solution for Pocketsats that we have. So about a month ago, we were offered the opportunity to fly on the Genesis mission. It's a mission by AMSAT that includes 2 Pocketsats to be launched December 10th on the Firefly Alpha launcher with a target orbit of 300 kilometers and 170 degrees inclination. And this accelerated our development of our Pocketsat solution. So we tried to develop a system that could fit their mission. There are 2 1.5P Pocketsats, about 300 to 400 grams, with 8 body-mounted panels and an average power of 370 milliwatts. And furthermore, they have passive ACS, just the permanent magnet hysteresis bars, and the payload volume available for us was slightly over half a P. So what does it mean for us? The requirements on the payload in this case that we had to make something that fits a 40 by 40 by 30 milliliter envelope, has an orbit average power of lower than 200 milliwatts, and a mass of less than 100 grams. So what do we do first? We first analyze the power budget, and sorry, 1 second. We first analyzed the power budget, and first we looked at the solar panel. So here you see a graph generated by IENAI 360, where we basically simulated the power available to all 4 panels and the total power. And we decided on doing 6 firings of 30 seconds every 2 minutes, once per orbit. This resulted in an orbit average power of 34 milliwatts. The power budget you can see below here, where you can take into account the transmission, the reception, which affect the power budget. And then here, the larger peaks is when we fire faster. We could technically fire more because we had up to 200 milliwatts of orbit average power available. But the problem is the following: since we have a passive ACDS, the best case we have is that we are aligned with the thrusters aligned with the magnetic field vector of the Earth, and in the orbit, the target orbit, only near the equator for a short period, the velocity vector of the orbit and the magnetic field vector are aligned. So it's basically counterproductive to fire when you're not when you're not aligned with your velocity vector. So in the end, we decided to fire only near the equator. And you can see here the alignment of the two vectors in this GIF. So that's why we reduced our firing window to such a small window. So regarding the attitude control, we simulated that as well. The attitude control system you can see here is basically the magnet and the hysteresis bar on the right. And in the graph, you can see the torques that are there, both the the disturbance torques, which are atmospheric and gravitational, and the magnetic and hysteresis torques. Particularly the atmospheric drag torque is particularly difficult to simulate. Here you can see some of the results. This is on the left, you can see the angular rates. The first picture, you can see the total angular rate of the satellite during detumbling. And it took about 76 minutes to get some kind of steady state. In the graph below that, you can see the three rotations around the three axes, around X, Y, and Z, where the frame of reference is shown to the left. And you can see that both the rotation around X and Z go to 0, while the rotation around Y, which is the roll, if you will, still has some value. So in first, at first this seems okay, but then if you look at the actual cone half angles in the plot to the right, and the one of interest here is the blue one, which is basically the cone half angle of the y-axis, which is the thrust vector. And you can see that even at steady state, it oscillates between 0 and 60 degrees, so you're never really aligned with the magnetic field, even, and definitely not aligned with your velocity profile. So what is the takeaway from this? Passive ACS is not sufficient for effective thrusting. It also needs fine-tuning, which is what we found. If you put too much hysteresis, your system will lag at the poles. If you put too little hysteresis or too large dipole, you will oscillate forever. And if you put a too small dipole, you will never be aligned with the B field. You'll have an offset, like a steady state offset. Furthermore, permanent dipoles can saturate hysteresis bars, and it's difficult to provide sufficient separation on a Pocketsat. And it's also difficult to shield sensitive components, electronic components that are sensitive to magnetic fields when using large dipoles on such a small system. So basically our conclusion is that if you want to fly a thruster on a Pocketsat, you will need to have active attitude control using reactor wheels or something similar. I believe Alba Orbital does that. So that would be, for example, a system that we could fly on if you want to have effective propulsion. So then on to ATHENA-π, which you can see in the pictures here. We're quite happy with it. The specs are the following. It consumes about 1 watt of power and produces 30 micronewtons of thrust. The ISP is about 3,800 seconds, and the efficiency is a whopping 56%. Furthermore, it has 500 milligrams of propellant, which is equal to about 200 hours operation. And the total mass of the systems is about 90 grams. The electronics we developed in-house are completely commercial off-the-shelf components. You can see some pictures on the right. The extra large cables are for programming the microcontroller, so they will be removed for flight, just to give you an idea. We've, and here also in the graph to the left, on the left bottom, you can see the basically measurements we do of the thruster operating, and here you can see the current emitted by the thruster as a function of time. And you can see it operates in both polarities, so it emits about plus minus 300 microamps with a 1 hertz cycle. And it does this, and it has quite steady operations. You can see the output is very steady. If you ignore the spikes, which are an artifact of the lab electronics we have. We've recently done an environmental test campaign, and now my slides are not. There you go. An environmental test campaign, a vibration test simulating the Firefly Alpha profile, and a thermal vacuum test with 4 cycles of minus 40 to 85 degrees at 10 to the minus 5 millibars, which were both successful. The system survived, although it has prompted us to make some changes to the fluidic system. So this is what we intend to fly on the Genesis mission now in December. So the takeaway of my presentation is various. I'll sum it up here in this slide. So we're IENAI Space. We do electrospray thrusters for Nano and also for Pico satellites. In December, we will fly our first IOD mission. And for us, the goal is to measure current and voltage and to prove operation in the space environment. We hope to have a commercial version for the end of 2022, which is next year. And that leads me to this graph, is what can we offer? Here you can see a plot of basically the altitude that the satellite is on, or the target altitude. And on the y-axis, you can see the mission duration. On the left is the two turquoise plots, which are for no compensation or ATHENA-π with 500 milligrams, the current version you saw. And at 300 kilometers, even with propellant, so with the thruster, the operation is not too long, but you can see at higher altitudes, it really makes a difference if you have a propulsion system. And if the satellite provider can afford us to one full P for our subsystem, then you can look at the purple graph, which has the y-axis on the right, and this is in years. So you can extend the mission durations from maybe 20 days to almost a year or a year and a half, using the ATHENA-π system. So this is very interesting, I think, for people who want to fly at low altitudes and do drag compensation. But of course, you can also use it at other altitudes for other maneuvers, constellation deployment, or any other kind, formation flying, any other kind of thing that you would like to do that you need propulsion for. Two other takeaways is electric propulsion needs active ACDS, so reaction wheels or something of that sort. And always ask about efficiency when you're looking into propulsion systems. And lastly, you can try IENAI Go at go.ienai.space. And I'd like to leave my presentation at that. Thank you very much for listening. And if you have any questions, I'll be happy to answer.